Welcome to lecture number 7 on measure theory. This is the second session on Lebesgue measurable sets. In the last session, we defined Lebesgue measurable sets. We gave two equivalent definitions. Okay. And today, what we are going to do is, if I have two measurable sets, their union is measurable, and hence by induction it will follow any finite union of measurable sets will also be measurable. Number one. Number two, we shall show that if I have a countable family En of pairwise disjoint measurable sets, then m star of union En equal to summation m star of En, which is same as summation m of En. But we still have to prove union En is measurable. Okay, today's thing is geared towards proving such things. Okay, let us get started. So let us quickly recall. E is a subset of R, is measurable. I am using Carathéodory's definition now. If for every any set F in R, we have m star of F equals m star of F intersection E plus m star of F intersection E complement. Notice that F intersection E complement is also known as F minus E. From F, remove all of E. Okay. Therefore, one can also write this as m star of F intersection E plus m star of F minus E. And since countable subadditivity of outer measure, this is always true. So to check measurability, we have to prove only this. Okay, keep this in mind because we have to use it many times today. Okay, the first thing we want to do is something very interesting. Suppose E is a measurable set and G is any set. Okay, assume U intersection G is empty. Okay, this is, call it the lemma. Okay, then we want to say m star of U union G is m star of E plus m star of G. But remember, since E is measurable, m star of E is same as m of E plus m star of G. That is, outer measure becomes additive if one of them is measurable. Okay, this is a very interesting result. It's a very trivial proof. Okay, so think of this. This is my E. Okay, this is my G. Okay, this is measurable, but this is not necessarily. Then I want to say outer measure of their union equal to sum of the outer measures. Okay, the trick is very easy. What you do is you look at this E intersection, the E union G. You want to say add, right? Now, if I take my test set F to be E union G, then what is F intersection E? Since E is measurable, I will use the measurability Carathéodory's definition for this measurable set E. F intersection E is E union G intersection with E. This is same as E. And similarly, F, okay, intersection F minus E, that is in U minus G, you remove E. Since G and E are pairwise disjoint, this is nothing other than G. You understand this? This is same as F intersection E complement. Okay, and F is E union G intersection E complement. That gives me only E intersection E complement and G intersection E complement. Okay, this is empty, whereas G intersection E complement is only, sorry, I meant F. Okay, F intersection E complement is E union G intersection E complement. This is E intersection E complement union G intersection E complement. Okay, this is empty and this is going to be only G. Okay. Right. Oh. Because remember, G is contained in E complement. Therefore, G intersection G complement is G. Okay. Right. I'm just going through it. Okay. So, in case you should not accept this kind of thing automatically. Right. Therefore, M star of F, which is M star of E union G. By definition, since E is measurable, this is same as this plus M star of F intersection E complement. But just now we saw this is M star of F intersection E is E and this is M star of G. But this is M of E plus M star of G. So we proved the result. So pause, review, proceed. So in particular, an obvious corollary is the following. Suppose A and B are measurable sets and A intersection B is empty, that is they are disjoint. Then M star of A union B is M of A plus M of B. Do you understand this? So this is my E, this is my G, therefore M star of U union G is what we did. That is equal to M star of E plus M star of B. But remember, A and B are measurable, therefore M star of A, this is M star of A plus M star of B, but that's M of A plus M of B. Okay? But notice that this we cannot write M of A union B. Okay, this we cannot write. Why? Because we do not know, okay, is measurable. This we do not know if it is meant. Okay. But what we know is this. Okay. Now let's look at a second thing. Now we want to extend this, call this as a proposition. Suppose EK 1K equal to N is pairwise disjoint measurable sets. F is a subset of R. Okay. So I have F. Okay. This is my E1. This is my E2. This is my E3. This might be my E4. Like that. Okay. These are my E1, E2, etc. This is E. Okay. Now what we want to do is a very interesting thing is M star of F intersection union EK, K equal to 1 to N. Can you guess what should it be? It says that this is nothing other than these values. We want to claim that this is nothing other than summation M star of F intersection EK, K equal to 1 to N. Please keep the picture in mind so that you will understand. Take the union, intersect with F, okay, there are a lot of disjoint pieces, right? So there it adds up. Okay, having picture is always good. And remember that even though we are dealing with R, I am drawing pictures in R2. Okay, it makes geometry clear, right? The proof is extension of the last argument. Okay, so let us start with this. Okay, so what we do is we take our set F intersection E1 union E2. This is our test set. Exactly like the last time. Okay. Now I will use measurability of U2. U2. Right? Then what will I have? M star of F intersection E1 union E2. This is my test set. Okay, this is equal to, if you want I could put a G anyway. So that is m star of F intersection E1 union E2, and then take intersection with E2. Right? You understand this? So I have E1 union E2. Okay, take the intersection and then take the intersection with E2. What I am going to get? I am going to get only m star of right, plus, let me write the second term. It's m star of F intersection E1 union E2 minus E2. This is using measurability. E2 with this as the test set. Right? Now let's look at what is this. This is going to be m star of F intersection E2, and this is going to be from U. This is E1 E2. You remove F2. Okay, you remove this E2. What I am left with m star of F intersection E1. Right? Please check these things theoretically. Just don't just go by only pictorial representation. You should also know this. Right? This is what we are claiming is F intersection E1 union E2 intersection E2 complement. Okay, this is, I know this, take this out. This is F intersection E1 union F intersection E2. Okay, this has to be intersect with E2 complement. Right? So this will be F intersection E1 intersection E2 complement union F intersection E2 and E2 complement. This is empty, therefore this is empty, whereas E1 is contained in E2 complement, therefore this is F intersection E1. Okay, please go through this kind of argument. Okay, because in measure theory, what many people do is there is a lot of set theoretic thing. Unless you have gone through a foundation course as we teach in MTTS, okay, you never check those things. Only Venn diagram, and so you always are very uncomfortable. Okay, please check this kind of stuff carefully. Okay, you may get bored if you are a good student. If you had already learned these things, you may get bored, but still, I request you to go through them. Okay. Okay. So we have proved the result for n equal to 2. What have we proved? M star of F intersection E1 union E2 is m star of F intersection E1 plus m star of F intersection E2. So what is the assumption here? These are measurable and pairwise disjoint. Okay. Now we want to extend the result to n. Okay, assume the result for n. So now I am given ek n plus 1 elements. What are they? They are measurable and they are pairwise disjoint. Okay. So what we do is we again do the same trick. That is, as a test set, what we do is we take F intersection E1 union En plus 1. Okay. These are test set. And apply the measurability criterion for En plus 1. Right? There you be applied for E2, here we are going to apply for En plus 1. Therefore, by measurability of En plus 1, m star of F intersection, let me write as union 1 to n plus 1 of Ek equals m star of f intersection union uk k equal to 1 to n plus 1, right? And this intersected n plus 1 plus m star of f intersection union uk k equal to 1 to n plus 1 and remove n plus 1 from this. Yeah? Do you understand this? Please pay attention. Now f en plus 1, now I am taking intersection of the n plus 1. Remember, these are all pairwise disjoint. Therefore, this is nothing other than f intersection en plus 1. Whereas this is nothing other than f intersection union 1 to n of ek. Because from this I am removing n plus 1. So just go to the picture. But try to write down the proof as I explained earlier. These are the various things. And if you want, you can put now en plus 1 separately. This is my en plus 1. Oh, it doesn't look nice, but anyway, sorry. Okay. This is en plus 1. Huh? And this is my set. Right? So let's look at that. So I am going to take f intersection en plus 1 and take only n plus 1. Okay. So of all these things, I have to take only n plus 1 thing. Only this will remain. And similarly, take all those things and remove n plus 1. All these, so e1, e2, en, these parts will remain. Okay. So what we have is this. Therefore, it is, is equal to m star of f intersection en plus 1 plus m star of f intersection union k equal to 1 to n. But what is this? This is by induction hypothesis. This fellow is nothing other than summation m of f intersection k equal to 1 to n. So we proved the result. So, okay, P or P. Let me again advise you, please go through this once more, draw the picture, try to understand, and then try to prove rigorously. Okay, that is f intersection union ek k equal to 1 to n plus 1, the whole thing. I intersected the n plus 1, that is nothing other than f intersection n plus 1, and similarly other one. Okay, please prove that. I already showed you how to do that in the case of 2, it's exactly the same argument. Okay, don't hesitate, don't assume. Okay. So now notice that if I have my, as a corollary again, okay, suppose my uk 1 less than equal to k less than equal to n are pairwise disjoint and measurable, then I want to say m star is additive on this. Finite, of course. What does it mean? That is m star of union k equal to 1 to n equals m star of k equal to 1 to n. But since these are all measurable, m star of ek is nothing other than m of ek. Remember, my measure m is restriction of m star to measurable sets. Okay. No, but here it is still m star. Notice that. Why? Because I do not know whether this is measurable. This is not clear. Measurability of this is not clear. That's why we have to put m star. Okay. The proof is easy. Exactly the same thing. Now take the test set f to be R and R itself. Right? Therefore, m star of R intersection union k equal to 1. This is nothing other than m star of union k 1 to n. Right? But this, according to the lemma, is m star of r intersection ek, but this is just ek. K equal to 1 to n. But this is nothing other than m of ek. K equal to 1 to n. So, this is clear. So, understand, we have to be careful. What we proved was m star is finitely additive on the class of measurable sets, but we still have not proved the union is measurable. Yeah, these are the small subtle things you want us to keep. If you keep on writing the proof, taking down notes, you will not understand these things. Okay, now is the crux of the matter. So we want to prove the major thing now. I will call it a theorem, but it's actually a lemma or a proposition. Let us assume A and B are measurable, then A union B is measurable. Okay, this is what I want to prove. Let me just check whether I am recording. Yeah. Okay. So this proof is highly geometric, but many books do not bring out the geometry. They only look at, we will use measurability of A taking this as a test set, we will use measurability of B taking this as a subset, and they keep on doing. Unless you remember what is the test set, you may not be able to do that. Okay, but I am going to give a very geometric way of looking at, okay, so that at any time you can prove this. In fact, not only one proof, you can give two proofs. Yeah, what is that? What do I mean by that? Let us go and check. So picture is very clear. So let F be any test set. Okay, then what is that I have to prove? I have to prove m star of F is greater than or equal to m star of F intersection A union B and plus m star of F intersection A union B complement. This is same as m star of F minus A union B, but this is same as m star of F minus A minus B. That is, I am claiming F intersection A union B complement. This we know is F intersection A complement intersection B complement. Therefore, it's F intersection A complement intersection B complement. From F, you remove A, remove B. Yeah? Is it clear? This is what we have to prove. These are all set theory. Okay? This is a digression. Okay, come back to this. Yeah? So the trick is, this one, this is the important trick. Let me write. The major trick is F intersection A union B, express it as a union. Okay, to which I can apply the measurability of A and measurability of B. Okay, remember this. I am going to give the picture. The picture is going to make life easy. So this is my A, this is my B, and this is my F. Right? Therefore, F intersection A union B, you can see this is going to be A union B is this, okay, and this is F. Right? But there are obviously three ways, right? Okay, this is one, and this is the second one. Okay, this is the third one. Okay, now what are they? Notice that this one is nothing other than I take A union B, intersect with A, but I don't want B. Right? You understand that? That is, this is nothing other than F intersection A minus B. I throw away B. Okay. Now let's look at this one. This one is F intersection A intersection B. All are common. It is in A intersection B as well as in F. Okay. And the third one is very clear to you, I'm sure. What is the third one? Third one is F intersect with B, but throw away the A part. When I intersect with B, I get all these things, but I'm throwing away the what is also in A. Therefore, it is F intersection B and A. Do you understand this? Therefore, what I have done is, I have done the following. F intersection A union B is F intersection A minus B union F intersection A intersection B and union F intersection B minus A. Yeah, is that clear? Right. Therefore, what I have is M star of F intersection A union B, right, equals equal to M star of F intersection A minus B. Do not worry about trying to remember the proof. Please follow the logic. Okay? Many times, whenever you are going through a proof, you think it's very complicated whether I can remember. Please don't do that. Your primary aim should be to understand. Equal to M star of F intersection A intersection B plus M star of F intersection B minus A. Right? Therefore, what I have is M star of F is less than or equal to M star of F intersection A union B plus M star of F intersection A union B complement. Okay, but this is less than or equal to, I am just writing this M star of F intersection A minus B plus M star of F intersection A intersection B plus M star of F intersection B minus A plus M star of F intersection, let it be right, minus B minus A. M star of intersection B minus A, I wrote it correct, right? Okay. So this I wrote as three things, just simply following this, and then this is M star of, this one is B minus A. This one I wrote this way. Okay. Please understand, you should never get confused. This fellow is this fellow. Okay. Now, what is that something interesting? Do you see that? Now I know B is measurable. And this I can use as a test set. You understand this? Right? So using measurability of B, I know this object, these two, let me just circle it. This is equal to M star of F intersection A. Plus, now let's look at this. Okay, this here I can use this of F intersection B minus A. I can as well write F minus A intersection B. You understand this? Again, please check. This is very easy. Okay, this is F intersection B intersection A complement. This is also the same thing, F intersection A complement intersection B. You understand that? So they are the same, right? Now, therefore, this fellow is, think of this F minus A intersection B. Now, use F minus A as a test set and measurability of B. Then what I have is, this is M star of B minus A. Yeah, M star of F minus A. Yeah, M star of F minus A. So use measurability of B and this as a test set. So they add up, right? Now Now you see that A is measurable. Use F as a test set. Okay. Measurability of A test set. Yeah, this gives me M star of A. Okay. Please go through this. So what I have shown, this one gives me measurability of this. Okay, therefore what I have is M star of union B. Yeah. Okay. Yeah, sorry. Last thing is, therefore this is M star of F. Right? Using measurability of A, I get M star of F. So what I have shown now, just go back. What I have shown is M star of F is less than or equal to M star of F intersection A union B plus M star of F intersection A union B complement, but that's less than or equal to M star of F. That means equality holds. This proves A union B is measurable. Please go through the argument. Yeah. So you can see I used twice the measurability of B, and the last minute I used the measurability of A once. Therefore, I proved M star of F is less than or equal to M star of F intersection A union B plus M star of F intersection complement of A union B is less than or equal to M star of F. Therefore, equality holds. Very good. But then in this proof, I grouped terms in such a way that I had to make use of measurability of B twice and measurability of A once. Right? Now try to regroup them in a different way so that you still get the same thing. M star of F is less than or equal to M star of F intersection U union B plus M star of F intersection complement of U union B. That's less than or equal to M star of F. But then in this, you should use measurability of A twice and measurability of B only once. That is, you have to regroup the terms in a different way. Look at the picture, look at the argument, go through that. Once you are done on your own, you will see you will never ever hesitate to prove this. Okay, this is a beautiful proof. Okay, many people I have seen in my life, okay, they come prepared, but when they go to lecture, either their memory is extremely good, they simply say, use this set to test the measurability of this, something you get inequality, some equality, some equality, some equality, add, you get. This is the way they prove. Okay, some of the popular textbooks prove this. I don't want to mention the name, but you can find it out. But with this, you will see. And again, notice that even though we are working with R, my pictures an R2, that geometric intuition gave me how to write a rigorous proof. This is very beautiful. Yeah, I hope you enjoy this. So let's go back. So what have we shown now? What you have shown is that A union B is measurable. Therefore, we have proved if A and B are measurable, then A union B is measurable. And this implies A intersection B is also measurable as a corollary. Why? Because notice that A is measurable, therefore A complement is measurable, B complement is measurable. Therefore, the union, this is measurable. Right? And this is measurable, therefore its complement, A complement in union, B complement. Complement is also measurable. But this is ACC, complement of A and double complement of B, but that is A intersection is measurable. Yeah? So P or P. And hence, it follows that if A and B are measurable, A minus B is measurable. That is from A, this is my A, this is my B. Remove that, this object is measurable. Okay, that is very clear because A minus B by definition is A intersection B complement, and A is measurable, B is measurable, therefore B complement is measurable, intersection of measurable sets is measurable, therefore this is measurable. Yeah. Now how do I use it? I would like to apply it somewhere to something which we already saw that. Right? Let us look at, we know that 0, 1, this is the interval, therefore it is measurable. Right? And we know Q is also measurable because it's a outer measure 0, therefore it is measurable. Therefore Q intersection 0, 1, call it A, this is measurable. And what is the measure of this set? M of A is M star of A, that's less than or equal to M star of Q, that is equal to 0. Therefore this set is measurable, measure of A is 0. Right? Now let's look at B, which is 0, 1 minus Q, which is same as 0, 1 A. This is nothing other than set of irrations. In 0, 1. Right? So I know this is measurable. This way, remember in the last session we proved R minus Q is measurable. That is set of irrationals is measurable. Now I am saying set of irrationals in any interval is going to be measurable. I gave the proof in 0, 1, but the proof is the same. Yeah? Very good. Now what I want to do is I want to know what is M of B. Right? But notice that A union B is 0, 1. Right? Okay. Now we had already seen that if an A intersection B is empty, then we have seen M star of A union B is M of A plus M of B. This was a corollary we did earlier. Right? But since A union B is measurable, this is same as M of A union B. But M of A union B is M of 0, 1. But outer measure of an interval is its length, therefore it's 1. But I know M of A is 0, therefore I conclude M of B is 1. Right? So pause, review, proceed. Notice that this result about B, I could not, I would have proved M star of B is 1. Because we know A is measurable and A intersection B is empty. Therefore, I know M star of A union B, which is M star of 0, 1, which is length of 0, 1, which is 1. But this we know by the earlier lemma, the very first lemma, this is M star of A plus M star of B. And M star of A is 0, therefore M star of B is 1. But what we did not conclude was that it is measurable. Now we are able to conclude. See, please appreciate this kind of result. It's not simply theorems and proofs. Okay? You should know how we are using. This result I could not have done earlier. I only know outer measure. Now I can confidently say B is measurable, set of irrationals in 0, 1 is measurable, and its measure is 1. Okay? Good. Now let's look at the main result of the today's session. Let En be a pairwise family of countable family of pairwise disjoint measurable sets. Okay. Then what we want to do is the following. We want to make two claims. One, M star of union En 1 to infinity, if you want to call it, is summation. It's the infinite series M star of En 1 to infinity, but that is equal to M of En. 2, notice that I am writing M star. I do not know whether it is measurable. So we want to claim union En, call it E, is measurable. Therefore, one reads as this. M of union En is m of en. Okay, this 3 is paraphrased. Okay, is we loosely say m is countably additive on the class of measurable sets. So we are nearing our final goal. So what we want to do is, if En is a countable family of pairwise disjoint measurable sets, their union is measurable. That we are going to prove later, but we will prove that M is countably additive on that. Okay, okay? This is a very important result. With that we will stop. Okay, let us go through the proof now. I hope I don't goof anywhere. Let us just go through it. So let us get started. So I have En. Okay, my Sn is union Ek. K equal to 1. Like partial sums, I am using partial unions. Okay, partial union. That's why I am doing it. Now let's look at, if we know that since these are all measurable, Sn is measurable because finite union of measurable sets is measurable. It follows by induction. Earlier we proved A union B is measurable, right? By induction, finite union of measurable sets will be measurable. Therefore, each Sn is measurable. And notice that Sn is contained in E, where E is union Ek. K, En, 1 to infinity. Right? Therefore, monotonicity, m star of Sn is less than or equal to m star of E. Right? Yeah. Now, next again, by monotonic subadditivity, countable subadditivity, m star of B is less than or equal to summation m star of En. N equal to 1 to infinity. Right? Now let's look at what is m star of Sn. Okay, this is same as m of Sn because Sn's are measurable. But we have seen these are pairwise disjoint, and we have seen that measure is finitely additive on pairwise disjoint family. Right? Therefore, this is going to be k equal to 1 to n of m star of Ek. That is same as 1 to n m of Ek. Right? Therefore, this is less than or equal to m star of E. Right? But this is true for all n. This inequality is true for all n. That means 1 to n m star of Ek, the LUB supremum of this is less than or equal to m star of E. But this by definition is the sum of the infinite series m star of En. 1 to infinity. That is less than or equal to m star of E. But by countable subadditivity is also less than or equal to m star of En. Okay, from here. Right? Therefore, you have shown that m star of E is summation m star of En. N equal to 1 to infinity. Because En's are measurable, I can replace the m star by m. It's the same. So we proved one. So PRP. Let me check whether I started recording. Yes. And in screen share. Right. Okay, good. Okay. The second thing is we want to show union En E equal to 1 to infinity is measurable. This is 2. Okay. Okay. So again we use the same kind of stuff. Okay. So let F be any test set, arbitrary set. Let us look at. Therefore, m star of F by, since Sn's are measurable, then I know this is equal to m star of F intersection Sn plus m star of F intersection Sn, which is same as F minus Sn. F intersection Sn complement, which is same as F Sn. Do you understand this? By this is because measurability of Sn. right? Okay. But again, remember we proved this ESN, this is, let me recall, this is M star of V of intersection union K equal to 1 to N and plus M star of F minus Sn. But remember what I called as a proposition? The proposition said, let me just quickly go through it. If these are pairwise disjoint, oh sorry, before that, proposition, I remember I wrote it as a proposition, yeah. If these are pairwise disjoint measurable sets, F is any set, then M star of F intersection, this is summation. Okay, so we are going to use this. Okay, therefore this is equal to summation M star of F intersection K equal to 1 to N plus, okay, I can say this is less than or equal to, okay, this is less than or equal to M star of F minus S. Remember, Sn is contained in S minus E. Okay, Sn is contained in E, therefore F minus Sn, okay, is I want to say greater than or equal to, right? Sn is greater than, therefore taking complement, I am removing a smaller set, therefore this contains F minus E. So this is greater than or equal to this, right? And again, this is true for all n. This is equal to, so the result is M star of F is greater than or equal to 1 to N M star of F intersection K plus M star of F minus E. Yeah, this is true for all n, therefore we know M star of F is greater than or equal to 1 to infinity M star of F intersection En plus M star of F minus E. But notice that by countable subadditivity, this is greater than or equal to M star of F intersection E. Right? Are you following? F intersection E is union of F intersection En. Therefore, by countable subadditivity, M star of F intersection E is less than or equal to summation M star of F intersection En 1 to infinity, right? Plus M star of F minus E. Yeah, but this is greater than or equal to M star of F always, again by countable subadditivity. Therefore, what do you think I have proved? I have proved that equality holds. What is the equality we wanted to prove? Again, please make sure you are understanding. We wanted to prove M star of F, whether it is equal to M star of F intersection E plus M star of F minus E. So, have you done that? So, this is M star of F intersection E plus M star of F minus E. Okay, so we have proved this. Please go through that. M star of F is greater than or equal to this. I have done this. Okay, so this is what we have to prove. This proves in the measurability of E. So what you have done is E equal to union En is measurable. Therefore, if I look at M from the class of measurable set to 0 infinity, okay, what are the properties does it have? It has M of an interval is length of the interval and it's countably additive. What does it mean by countable additive? I have to start with a pairwise disjoint family of measurable sets. That is the elements of countable. Then I have that. M of union En is summation M of En. Okay, this all you are done. As I keep saying, do not try to remember the proof. Okay, please go through it. Try to understand where we are using and try to follow. That's very important. Many times what I find is students try to remember the proof. Okay, when they are going through the proof, they are not trying to understand the proof. They begin to doubt whether they will remember the proof. Okay, that is detrimental. Try to understand, you will see slowly, you will have confidence, you can write the proof on your own. Okay, stay tuned. There are a few more things which you have to talk about measurable sets. We will do it in the next session. Thank you very much. Stay safe. We will meet again.